Welcome to Equilibrium Constants, where we're going to talk about Kc and Kp. We'll talk about their purpose and how they were derived, as well as some simple examples. So after this lesson, you should have a greater understanding what dynamic equilibrium is. We've talked about it already, but this is sort of a way to talk about in chemical form and let you experiment with some chemical forms of it too, using a simulation. You should also understand why we have a need for this equilibrium constant and how it comes about, and how to find the formula for it. Near the end, we'll do some simple examples where you'll find the formula for it, as well as some simple calculations with it as well. So before you move on in the video, there's an activity that I want you to do. I want you to go to this website that I have up here and launch the simulation. This has actually 3 simulations in one, and I want you to go to the top right area and click on Rate Experiment tab, and then play with this a bit. So I want you to play around with it a little bit before we do some directed guided experimentation so that you kind of see what's going on. But to direct your attention on what you want to pay attention to, because there is a lot going on in this simulation, I want you to pay attention to the ways that the ratios between the products and the reactants end up based on a starting position. I would also highly suggest that you put up a bar or a pie chart that are in the little options box so that you can see how these change as the experiment continues. Now, there's a lot of other things going on here, temperature, just a lot of things about speed that we're going to learn when we do the kinetics chapter. So for now, don't worry about those. Just notice what's going on with the concentrations at the beginning and the end of the reactions. Okay, so I just put the screen in to give you a bit of a time for you to pause so that you can go do this. And I really want you to do this before this next part so that you have time to work on it on your own. Now we'll do a little bit of directed exploration where I'll sort of walk you through some things that I want you to notice about it, just in case you didn't notice them on your own.
So hopefully in your experiment you noticed a few things. First of all, if you don't have enough of one of the reactants, say A, you don't get very much of the products, regardless of how much of the other reactant that you add. You must have enough of both reactants. Also, because this is a reversible direction, you can start with what we would call in the setup the products and get the reactants. The 2 reactions are going back and forth. The final ratios aren't the same for all starting conditions. So you can't directly relate the amount of A to the amount of one of the products. It depends on both the reactants. When we open this is the screen that it gives you, and hopefully you followed the directions and went up here to rate experiments. Now, what I was talking about with the pie graph or the bar graph is to come here and put one of these 2 up. Sort of depends on whatever you like on which one you put. Now, you can go ahead and when you were playing, you probably found that you could add some molecules like this. And then you could go ahead and add the other quote-unquote reactant here. Then you could let things react. Now, when I did this, I got a little impatient and I raised the temperature. It just kind of makes everything go a little bit faster. And you could restart these up. And you can watch the AB kind of show up here and the C show up here. Or if you had the bar chart, you can do this and you can watch the products start to show up and you get this sort of ratio coming up. Now, playing around like this is great, and it shows you what happens if you add, say, a lot of A, and then what happens to these. And you see how A is much larger still. Again, if you prefer, you have this. And then what happens if maybe you add a lot of one of the products. And what happens to the adjustment there. Okay, now that is all fine and great for playing around and doing some noticing, but I want to also show you that you can set it up to be a little bit more controlled. You can start with a certain amount. So you could start with 10A and 10B. And then go ahead and start the experiment and watch what happens. And you can see if you do this and you actually let it all come to equilibrium, depending on exactly what your temperature is, you end up with about down here 6644. It oscillates back and forth a bit. It's about that. And you could change this to 20 and leave that at 10 and see what happens. You did that, again, depending on about what your temperature was. I ended up with 16,644 when I did this before. Now, if we're trying to draw some actual calculation conclusions from this, it's a little hard to do with this small of numbers. You notice this oscillates. Even once you've let it go on for, 5 minutes or so, and equilibrium is definitely established, this is doing some oscillation. And that's just because the dynamic equilibrium is setting up, so it is constantly changing. And when you don't have that many molecules to begin with, you're going to see these oscillations. Now, you can also go ahead and put a lot more. So I wanted to draw some conclusions from this and help you draw some conclusions for this. So I started with 60 of each of the reactants. And started it up. So now you see there's a lot more going on here, and these numbers are still oscillating, but percentage-wise they don't oscillate quite as much. So when I had done this before, and it looks like I'm relatively close temperature-wise to when I did it before, I ended up with about 34, 34, 26, 26. Then I went through and I changed this, and I put this up to 80, and this up to 40. You'll notice I kept all of these constant at 120, and that was just so that the pressure stayed constant. And I wrote down these numbers after it all equilibrated. And then I went through and changed it to 120. And I did the same thing. That's all we got. Let it equilibrate and wrote down the numbers. So with all of these, you see that there's a huge difference over here on what these numbers equal. So we need a way to describe the equilibrium conditions here. We want to be able to use some sort of mathematics to decide how much of each substance is going to be around if we know some of the other concentrations. So let's head back to the PowerPoint and see what we can get there. So now let's look at the results of this experiment and see if we can find any common results regardless of what the starting conditions were. If you look at these numbers, we can't simply take the starting amount of A and relate it to the ending amount of A, the starting amount of A and relate it to the ending amount of C. You have to look at all of them combined. So play around with these numbers a bit and see if you can figure out an amount or some form of number that relates all of these together. Alright, so let's look at this experiment one more time and these values one more time. And if we have this reaction, this equilibrium reaction, and we take all of the products and we take all of the reactants and we relate them together. We can take the two products that we have and multiply them together, put them over top of the two reactants we have multiplied together, and we see that we get a relatively constant number. Now, of course, because we don't have a huge amount of molecules here, there's a little bit of variation, but the more molecules you would have, the more you would see that this stays constant. This relation, this is called Kc. So Kc is products over top of the reactant. In this case, AB times C over top of A times BC. Now, in the example in the simulation, all of the stoichiometric coefficients were 1. What about in situations where they aren't? So let's take a look at a very generic example. If we have this reaction, we could also go ahead and write that a bit differently. We could write it like this. Now, obviously that's not how we would normally write it, since it's kind of long and hard to see, especially for complicated reactions, but there's no reason why we can't. So let's write Kc out the same way that we did before. So we would have that. Now, of course, this would seem silly to write A times A when we could just write A squared, or C times C when we could just write C squared. So let's do a little bit of rewriting, and we would get this. So we can see that whatever the coefficients are in the reaction, those become the exponents for the concentrations of Kc. Now, everything that I've said about concentrations, which is all we've been talking about so far, is true for gases as well. Only now we're going to use pressures instead of concentrations. And therefore, when we use these pressures, it's called Kp. So, same rules apply. You're going to put products over reactants. It's just you'll write pressures now instead of concentration. You're still going to raise each pressure to its stoichiometric coefficient. Now, something that you should also notice, which we haven't come across yet, is you're only going to include gases and aqueous species if you're doing pressures or concentrations. You're never going to include a liquid or a solid. So for Kp, you include pressures. For Kc, you include aqueous species. And you're never going to fill in any sort of value for a solid or a liquid. Okay, here are a couple of simple examples. It's a good idea to pause this now once we put these up and see if you can get the correct answers without help, and then continue on to see if you have the right answer. So let's look at the first one. We're going to write out all of the products over top of the reactants, including all of the coefficients as exponents. So if we do this, we would get this. So you can see all of the pressures are included, and we've raised them all to the coefficients. Now, try this next one on your own first. Pause this if need be. Okay, now before I show you the answer, did you remember to check your phases? Remember, we don't include anything that's a solid or a liquid. We only would include gases since we're doing Kp. So if you didn't check this, you should go back and check your answer one more time. So since we are only including gases, this leaves us with this. Okay, now let's do an example that has you calculating a number for Kc as opposed to just filling out the equation. The simplest form of these calculations are going to be when you can measure the partial pressures or the concentrations of the gas or aqueous species respectively, and then you would just fill those in and you would solve for Kp or Kc. So let's take one similar to what we did in the last slide. So this is the equation we had in the last slide, and we determined that Kp is going to be this. Now, since we already know since we already know the pressure of CO2, we can fill that in, which means for Kp we would get 1 over 2, or 0.5. Now, you'll notice that I don't have a unit on this value, and that might seem a little weird since we're used to always having to have units, and we know that pressure has a unit. I'm not going to get into this too much right now, but what we're actually filling in is something called an activity, and this is unitless. It just happens to be that it's the same value as the pressure. So for right now, don't worry about it too much. We'll talk about that later. Just know that Kp and Kc aren't going to have units when you solve for that number. So just don't put any units there and you'll be fine. So now we can move on to more complicated examples where we have a certain amount of a reactant, and then when we're done, we're going to have another amount of a reactant. So I have it set up so that we have 1 gram of diatomic iodine, and then when we heat it up, we're down to 0.830 grams. So what we're going to do is we're going to go through and we're going to say, well, how much of it did we start with? How much of it did we end with? And then what does that mean about how much of the I do we have? So before we can start this, we have to convert these grams into moles per liter, because when we're dealing with Kc, we have to have concentration. So when we go to do this, we'll start with 1 gram. We'll divide by the molar mass. To get how much we had. Now remember, we want concentration, so we're going to divide this whole thing by 1, which keeps the number the same. So we have this concentration. Now that was initially. We also know how much we have at the end. So we'll do the same thing. And again, divide by 1 liter. And that's our final.
Now from here, we can go ahead and we're going to make an ice chart. So now that we have these new values, we can fill them into an ice chart, where I stands for initial, C stands for change, and E stands for equilibrium. We know the initial and equilibrium values of I2. So we'll fill those in now. These are from the previous slide. And remember, those are molarity. Now, because we know the initial and equilibrium, we know what the change is as well. We'll just take the initial value and subtract the final value. Now, if we know that the I2 has changed by that much, we will look up here and see that, well, I must change by twice that. And the initial concentration of that I is 0. So this means that our equilibrium value for I must be like that. From here, we can now solve for Kc, since Kc is products over reactants. We can fill these values in. To get our final value. And because it's Kc, there won't be any unit. Now there are two more topics about Kc that we've been alluding to and need to cover explicitly. First, we know that Kc can be calculated from final conditions, but what does just having that number tell us? Well, we can see what is favored simply by looking at this number. Is Kc greater than 1? Is it less than 1? What does this have to do with the amount of products and reactants? So first, if Kc is greater than 1, let's look at the equation and see what that means. If Kc is greater than 1, does that mean that we have a higher numerator or a higher denominator? Well, it means that the numerator must be larger than the denominator. This is larger, the numerator is larger than the denominator, so Kc is greater than 1. So that must mean that C and D, in this case, are larger than A and B. So products are favored. Now, conversely, if Kc is less than 1, that means that the denominator must be bigger than the numerator in order to make Kc less than 1. So if the denominator is bigger, that means that the reactants are favored. Now, I've mentioned several times that K is a unitless quantity. Let's look at why that is now. When I've been telling you to fill in the concentrations or pressures into the Kc or Kp equations, what I've been telling you isn't actually 100% true. What we've really been filling in is something called activities. Now, for Kc, and therefore concentrations, what this means is for whenever we fill in a concentration, what we've really been filling into is the concentration over top of 1 mole per liter. When we've been filling in pressures, what we've really been filling in is the pressure that we have over top of 1 atmosphere, 1 Pascal, whichever pressure unit we've been using. Now what this does is cancel out the units, and this makes K unitless.